So I have started the recording. Let me start sharing. So today we're going to be covering the so far what we've done is we've done the organic and the organic naming, the organic pathways, as well as the chemical analysis of organic molecules. Today, we're going to be dealing with instrumental analysis. Essentially, these are tools that we use, right, to analyze a specific chemical. Yeah. Now, the big thing that I want you to realize is that they won't get you to deal with these individually. Analytical techniques are used to work together. So whenever I introduce an analytical technique, I want you to think about it in context with all the other analytical techniques, right? Like, let's just say I give you one that helps you find the mass of the object, right? And I help you find another one, which helps you find maybe the bonds that are present in the object, yeah? See how those two work together in order to help me find out what the molecule could be here? So, we'll start going through this one. So, the first thing that we're going to be dealing with is going to be mass spectroscopy, yeah? So, I'll highlight the phrase base peak and molecular ion peak, or they'll call it a parent peak sometimes. There is a okay, so that's fine. Yeah, this one. Okay, back. So there's a base peak, the molecular ion peak. I also want to point out this mass to charge ratio. Yeah, M to Z refers to mass to charge. Turn my mic back on. Okay. So those are the things I wanted to point out. So those are the two things. So here, base peak is the most abundant ionic fragment, and we're going to discuss the idea of the ionic fragment as well. Yeah. We also have the molecular peak, which is the highest peak that's present. So let me just start getting into this one. So this is what a mass spectrometer does. Yeah. Essentially, what you can think about it as, it shoots an electron into like a sample of particles. Let's just say these particles contain like, let's just say methane. Yeah. What's happening here is that they're shooting electrons into it. Yeah. So they're shooting electrons into it, and they're trying to knock off an electron from this compound. So here, right, what's happened is that, well, they started with the CH4 and they've shot an electron into it. And once they've shot an electron into it, they're trying to knock an electron off. So they've knocked an electron off here, yeah? So now this molecule is positively charged. You can imagine like one of these hydrogens, because this is what the hydrogen would look like. You can imagine one of these electrons from the bonds is being knocked off, yeah? So now this hydrogen is positively charged. Here, the product is 2 electrons. So I don't want you to confuse this one with redox chemistry. It's not donating. We're intentionally knocking electrons off here. Now, what this does is that afterwards, it goes through, like here, it's going to interact with a magnetic field. Now, you don't need to know this part, yeah? But essentially the idea is that the magnetic field affects the charged particles, but not the non-charged ones, yeah? Non-charged ones aren't affected by the magnetic field. Charged particles are affected by the magnetic field. So here, this charged CH4 plus, remember I'm using the brackets around the plus, I want you to do that. So here, Yeah, they're going to go all the way around. Yeah, and they're going to hit at different places on the detector. Now, the place that they hit on the detector is going to be based on their mass. Yeah, the larger the mass, like different masses will hit on different places, and this allows us to create a mass spectrogram. Yeah, this mass spectrogram is what you need to know how to understand. So I'm showing you this one. You don't need to know the apparatus here. Yeah, you don't need to know how this works. It's just very nice to understand. Well, here is how the mass spectrum works, and here is how, like, here's the graph. Here's how it creates the graph that we want. So here we have an electron getting knocked off. It gets accelerated through a magnetic field, and the magnetic field hits the detector in different places, depending on its mass. So, yeah, you won't find any neutral fragments in here. So I specifically mentioned that they had to be charged. We don't have non-charged particles don't get affected by a magnetic field. If any of you guys have done physics before, you'll know that, like, B equals F equals BEV, yeah? If there's no charge, right, there's no force as well. So, but you don't need to worry about that idea. You just need to know that you're only going to find charged compounds in your mass spectrogram. So here, right? This is the mass spectrum of ethanol, yeah? Here, they've labeled the two peaks. The base peak is the most abundant peak, yeah? So it's the peak with the highest abundance. And here we can see it's about 29, yeah? So it's 29 mass to charge. Over here is the ion peak, yeah? And this ion peak, it looks like it's at 44, yeah? So that's the ion peak that's occurring here. And it's the largest peak. Now you're probably like, well, that's the largest over here. And we'll discuss that in 2 seconds, yeah? First, I want to discuss what the base peak tells you. The base peak tells you the most abundant fragment. So here, they've just lost an electron. But, like, if I draw out my structure for ethanol, right? This is what my ethanol looks like. Imagine instead that I break the bond here, yeah? And what's going to happen then is I'm going to just be left with COH. And it's going to be charged because they're going to be this. We've lost an electron here. We've effectively, by cutting off that bond, we've lost an electron. So this becomes this charged compound, right? So we've basically broken the bond, and now we're left with this charged compound, right? If we calculate the molar mass of this one, it should be 16 plus, yeah, so 28, 29. So here we can see that this could be a fragment that causes this base peak, yeah? The reason being is because the molar mass of this compound is 29, yeah? Which corresponds to the mass to charge ratio. Because here, the mass to charge is going to be 29 to 1, yeah? Because there's a charge of 1, there's a mass of 29. So, now, the key word is that it could be a potential peak that causes this, yeah? There could also be something else in the compound which creates this mass to charge ratio of 29. But it's most likely going to be the C double bond OH. We can't be completely certain. So whenever they ask you what is a possible compound which creates this mass to charge ratio, it just needs to be a compound which makes sense in context with the rest of the compound. For example, I can't have like C H H O, right? That doesn't make sense, right? Because there's no CHH bonded with an O over here, yeah? So, does that idea of the base peak make sense? Yeah? Does that idea of the base peak make sense? Is that all good? Thumbs up, thumbs down, thumbs to the side, thumbs all around. Yo, what's up, Mia?
Sorry, I didn't mean to press that.
That's all good. Oh, reactions don't work? What? Oh yeah, it's because of the griefing. Let me change that real quick. Yeah, send reactions. There you go. Try send reactions down. Okay, perfect. Now they're working. She turned off your ability to screen share so we don't have another griefer situation. So that's the base peak. Now the ion peak is essentially, right, the compound itself after it's lost a single electron. So here, this has a mass to charge ratio of 44, yeah? Which is equal to the molar mass of this one. This one's also 44, yeah? And what that tells, like here, the ion peak just tells you, the ion peak effectively tells you the molar mass of this compound, yeah? That's the goal of the ion peak. It tells you the molar mass of the compound. So, now, I'll talk about this. I'll talk about this thing in a second, yeah. But it tells you the molar mass of that of this specific compound. The molecular ion peak. It tells you the molar mass of this specific compound. Now, I want to discuss this peak here, yeah. Because so how can this get to 45? Well, here we want to think about the fact that there are different isotopes. There were different isotopes of carbon and hydrogen. This could be a carbon-13 isotope, which causes it to have a mass to charge ratio of 45, right? Because now the mass is 13, not 12. We could also have a hydrogen that has a mass of 2, yeah? Because there's an isotope of hydrogen that has 2, yeah? So that's what causes this little peak over here, yeah? And this part tells you the relative abundance of specific isotopes, yeah? So here, there's definitely more regular carbon dioxide, or carbon and hydrogen compared to the isotope versions 13 and 2, yeah? So, does the molecular ion peak make sense to everyone? Is that all good? Okay. What about Mia, Emeth, Blessing? Okay. So, again, they've already done this mass to charge ratio. And just for the explicit context of the VCE, we only deal with the ions with charges of 1. You can have a compound lose more than 1 electron, but we don't tend to see it, and we don't, because we're looking at the graph. We can't really tell. Like, for example, let's just say over this 44, it could totally be something that has like a molar mass of 22, right? 22 with a charge of 2, but we usually just think about having a charge of 1, yeah? So here is the mass spectrum of propanoic acid, and it just emphasizes here the presence of different isotopes of carbon which cause these different peaks, yeah? Because we know propanoic acid, it's going to look something, it's going to be like this. So CH3, CH2, COOH, yeah? So here, this propanoic acid is going to have 24 plus 30, 36 plus 32 plus 6, which is going to be 42, 74, a molar mass of 74, right? So it makes sense for it to have a peak here, but it doesn't make sense for it to have a peak here unless we have that isotope. So that's one thing you want to be careful of. So what am I getting out of the mass spectrum? I'm essentially just getting out what the molar mass of the compound is, yeah? The base peak tells me what the molecular peak tells me what the molar mass of the compound is, yeah? Whereas the base peak tells me the most abundant. So we have here the base peak over here. We also have one over here, yeah? So here, right? We'd only have, this one's taller, so this one's the base peak. Okay, technically for this compound, the molecular ion peak and the base peak are the same. So here, this is just going to be CH3, CH2, why is my pen not working? COOH plus, yeah? That's what this compound's going to be. Any questions about that so far? Any comments, any concerns? All good, thumbs up. Like, wait, how do you determine it? What do you mean, how do you determine it? What's the molecular ion peak? Oh, the molecular ion peak is the highest one, yeah? So it's the one with the highest mass to charge ratio, yeah? We don't consider here, technically both of these are the molecular ion peak, right? But we usually just consider the one with the small, like, well, the regular isotope as the one with the molecular ion peak, yeah? Whereas the base peak is the tallest one, yeah? So here, this one's also the tallest one. Does that make sense? So, here, what fragment must have been lost from the molecular ion to account for the height at 45? So here, can someone tell, I'll ask Sway, what do you think was lost so that we could have this mass to charge ratio of 45? What do you think was lost out of the parent one? Actually, I'll ask you this, yeah? What is the parent ion? Are you able to unmute or hello? It's not letting. Oh, okay. It's not letting you unmute. Let me unmute you. Wow, I really put a lot of restrictions on you guys, didn't I? Hydrogen is lost. No. Yeah. So essentially, a hydrogen is knocked off. Yeah. So here we have the molecular ion peak here. So we have this CH, CH2OH plus. Yeah. It's either this hydrogen can be knocked off, a hydrogen over here can be knocked off, a hydrogen over here could have been knocked off, and that creates this peak here, or could account for this peak. So technically, we could have this one accounting for it. We could also have this one accounting for it, or we could have this one accounting for it. So those are the ones we could have. See, I want you guys to see that I'm putting the brackets around these ones. Yeah? So I'll keep any questions about that one? Is that all chill? Okay. Well, it says you can. Right. Turn on the microphone. You have the privilege to turn on your microphones. I don't know why it's not working. Anyway, I'll keep going forward. So here we have one of ethanoic acid. Yeah. Uh, I just want you guys to type in the chat. What do you think the base peak is, and what do you think the parent peak is? Just type it in the same message. What do you guys think the parent peak is, and what do you guys think the base peak is? Oh, wait. You guys have permission to type? Yeah, base is 43. Ion peak is 60. Yeah, that sounds about right. Anyone else? Everyone else agree with Soyam? Yeah, perfect. Okay. Is that all good? Thumbs up, thumbs down, thumbs aside, thumbs all around. So, which species is responsible for the base peak? Is it A, B, C, or D? What do you guys think? What do you guys think is responsible for the base peak here? Is it here the base peak has? Yes. The base peak has a really weird mass. Okay. What do you guys think? Is it A, B, C, or D? Is it A? Is it B? Is it C? Or is it D? So D, 1C. Any other guesses? Have another D. Okay. So here, this has a peak at 55. Yeah? Which means the mass to charge ratio must be either 55 over 1 or it could be 110 over 2. Yeah? So here, right, if we look at compound A, well, this one, like these two together have a mass of 55 because it's 48 plus 7. And then we add the chlorine, yeah? Here, we don't consider chlorine having its regular molar mass of 35.5 because that's a ratio of its relative abundance. We just consider it as 35. So either say 35 or 37, yeah? We're going to assume this 35 because it's the most abundant one. So here, this one has a mass to charge ratio of 90, yeah? Over here, this one is going to be 36 plus 4, which is 40. 40 plus 35. This is going to be 75. This one over here is going to be 36, 36 plus 5, which is 41. And then this one over here is going to be 55. So here, D is the answer. Does that make sense? So I'm just using... Yep, what's up, Email?
So do we just disregard like the decimal places when we're doing like these type of calculations?
Yeah, no, not disregard the decimal places. It's more or less you understand that there's two isotopes of chlorine, yeah? We use the isotope of 35 when doing this, yeah? Whenever,
Yeah.
for bromine also has a similar thing. So bromine has a 79 variant and bromine has an 80 variant as well. We generally use the 79 one, right? So I just want you to remember that isotopes can affect, like, for example, we could have another, like, we should expect another peak at, like, if this one contained a chlorine, yeah, we should have expected another peak at 57, right? Because that represents the second isotope, adding 2 more to that mass. Is that all good? Does that make sense? Okay, we have Swan, Myth. What about me? Kavini, Blessing. Does it all make sense for you guys? Some crazy organic stuff. So, oh yeah, here are some disadvantages. You need to have a pure substance. If you don't have a pure substance, then it sort of just messes with it all. It doesn't tell you anything about the structural information. It only tells you about the molecular mass. So here, I want you to remember, mass spectrum only tells you really about the molar mass. It doesn't tell you about the structure, yeah? So even though we can think of potential structures, it won't give you a direct structure, yeah? It's not suitable for non-volatile, so basically anything that can't ionize easily. We need to be able to shoot the electrons off it. So let's just say if it has a really strong attraction to its electrons, it's going to be very hard. And the thing is, it's a very destructive technique, yeah? Now, I've never seen this one be actually asked in the exam before. They more focus on A, they more focus on asking about B, because they're about analyzing them, organic compounds in context to other techniques, yeah? And these other techniques also analyze organic compounds. So does that make sense, everyone? Is that all good? Any questions, comments, concerns? Okay. So here, which information can be obtained from the mass-to-charge ratio in a mass spectrum? The molecular mass of the compound, the number of carbons in the compound, the compound solubility, the compound's boiling point. Which one? You have an A, you have another A. Anyone else giving out an A? An A. Everyone gets an A. So here, the answer is just A. We haven't spoken about these two, and we haven't spoken about any of these three. The only thing we've spoken about is A. The molecular ion peak is produced by a negatively charged ion, the ionization of the parent fragment, a neutral compound. Two people say C. Another person say C. Another person say C. You guys are all wrong. It's B. Right? So here, the molecular ion peak is in a fragment. Yeah? The molecular ion peak is a fragment is like, let's just say if we have CH4, yeah? A fragment of this one is going to be CH3 plus, yeah? CH4 plus is not a fragment of itself, yeah? Right? All this is saying is we've lost an ion. A fragment, we've lost an actual element in here. So here, the answer is B. So it's the ionization of the parent molecule. Does that make sense for everyone? So it's not a fragment. A fragment loses an element or something, yeah? So here, the species that produces the molecular ion peak in the mass spectrum of this compound is, what do you think would produce the molecular ion peak? Is it A, B, C, or D? What do you guys think? We have one person saying A, we have another person saying A. Anyone else? Any other guesses? A. Right from Mia, blessing. A. A, yeah. Here's A. These two are negatively charged, and this one here, right? Because it's 2 plus, the mass to charge ratio here is going to be 15, 15, 29, 29, 29 is 58 plus 32 plus 12, 70, 70, 102, yeah? So it's going to be 102 divided by 2, which is 51, which is smaller than this one here, yeah? So even though this could be a fragment that's, this could be a fragment that's present, or a molecular ion that could be present, it's not the molecular ion peak, yeah? So here, consider the mass spectrum for propanone, yeah? Which species is responsible for the mass peak at 58? So which one of these is responsible for the mass peak at 58? What do you guys think? Wait. What's up? So basically, the change can have coefficients. Yeah, the charge can have a coefficient to it. We like as I said before, it can like you can have multiple ionizations. We just don't tend to consider. We don't tend to think about them in VCE. So ionization being like it can lose electrons in multiple times. Yeah, but we don't really think about that much. We don't think about it that deep in VCE. The deepest we think about it is like with the idea of the halogens and no, the idea of the halogens as well as the isotopes of those halogens. So what do you guys think the answer is? It A, is it B, or is it C? We have one person saying D, we have a second person saying D. Come on, Emeth, Kevin, yeah, it's a D. Blessing, what do you think? I think it's D as well. Is it maybe A, C, D again? So this one is 15 plus 15. Oh wait, so 15 plus 15 plus 28. Yep, it's D. It's not C or A because they're non-charged, and this one's molar mass is too small. So what is the fragment that could be responsible for causing the peak at the M to Z ratio of 15? What do you guys think? Is it A, B, C, or D? Yep. So here, it's just A. In mass spectrometry, what does the term qualitative analysis refer to? I want you guys to remember qualitative analysis. What does qualitative mean? Right. We have one person saying C. B. C. So here, I want you guys to remember that qualitative analysis refers to identifying, not quantifying. So here, we don't like we can quantify the relative abundance of isotopes using this technique. But that's a quantitative analysis because we're quantifying the abundance, yeah? We're quantifying the boiling point. We're quantifying the concentration, right? We can't even find B and D using this. So the answer is only C, yeah? Does that make sense? Mia, does that rectify everything that you said? Because we can determine the relative abundance, right? Because let's just say we have one peak that's like, you know, this height, and this peak is this height, and this one's 3 times this one, yeah? That means the abundance of each isotope is a 3-to-1 ratio. So now we have IR spectroscopy. IR spectroscopy. The only thing that I'll be mindful of is this unit wave numbers and the idea of transmittance, yeah? So the amount that passes through the substance, as well as the idea of this fingerprint region, which I'll mention in more detail later. We don't talk about absorbance here, we only talk about transmission. Any depths? No, not really. I wouldn't say any depths. Like it's more like can you use this than definitions. So, the point of this slide is essentially what IR spectroscopy uses is that it shoots IR or infrared light into a compound, and this causes its bonds, right? the bonds between compounds to like move. Sometimes they can stretch, sometimes they can bend. I remember there was like, it's like this, and there's like this, and there's like this. If you guys are ever interested in how they can stretch, there's probably some great videos out there. But essentially, it hits the bond, right, and it causes it to like move. And that movement is how we determine the IR stuff. Yeah. So, like different, like you can think about it as different bonds will move in different ways, or will move in different wavelengths of light. So, before I begin yapping on about this, everyone has their best friend, right? You need your best friend. Your best friend is your only friend, right? You don't have any other friends. You only have this best friend. That's it. So let me just pull up here. I'll pull up where is it? It's down here now. So this is the table for the IR spectroscopy is, yeah? So here, have they removed something? No, okay. Oh, no, they've added. So here we have all of these bonds that could be present in organic compounds, which could help us find the different functional groups that are present. Yeah? So here we could have like these are the ones for the amides, or like this is the C double bond O's. These are the OHs. I want you to be mindful with the OHs, so we'll have a look at them. We'll have a look at them in a bit. All of these should have a CH, and here's the NH. So basically, right, this is like the wave number is the length that it should spread across on this graph. Yeah. The other thing that I want to point out here is that because these two are very close and overlapping to each other, we have to, if we identify an OH group, we either have to identify as OH acid or OH alcohol. Yeah. With the C double bond O, we don't have to do that. Like, we don't have to call it OH amide, because we can't tell an amide apart from an aldehyde, apart from an acid, apart from a ketone, apart from an ester. And you're probably like, well, please, in what context am I going to have to do this in? I still don't know what the freaking graph looks like. So let me just, like, switch to this. So here, this is what the graph looks like, yeah? And what we can see here is that we can see a peak at around 3,200 to 1,000 to about 3,600. Yeah. So it's about 1,200 to 3,600. Yeah. We have another peak over here, right, which is about like, let's just say like 650. Oh wait, no, 750 all the way to like 1,400. Yeah. 1,400, sorry. What is the distance between those two? Wait. 1, 2, 3, 4, 5. Okay. Wait, so this is 600. This is about like 800 over here. Yeah. We can see another peak over here. And essentially, right, by using these peaks here, it can help us determine what's present. So if you look back on your data book, I want you guys to tell me what this peak over here could represent. What do you guys think? Looking at the data book, looking at your data book, looking at the Z data book. So it could be NH. Any other guesses? Anyone else want to take a guess? Yep, just wait here. No. So here, right? I want you to look at the data book. And here, an acid would stretch all the way from here to here. Yeah? So an acid would have this very broad peak. This is what we characterize as an OH brackets alcohol. Yeah? They're different enough where we can differentiate them apart from each other. Yeah, so OH alcohol here. Yeah? It's not a like for example, Swayham put NH, yeah? It's not an NH because this is what the NH is, and that's like way too small for what we want, yeah? That goes to the peak. Whereas this one, the OH, right? It goes from here to here. I'm not giving you any shade, I swear. It's just like I wanted to point that part out. Why it's not an NH and why it's an OH one, yeah? And it's not a acid, it's not an OH acid, yeah? Because the OH acid peak is so much broader, yeah? It's huge, it's massive. It's like the low taper fade mean. So, these are just some of the things that we're going to look for. Most of the peaks that you're looking for are going to be just strong, yeah? Yeah, shut up. Most of the peaks you're looking for are going to be strong, yeah? But sometimes they'll get you to, they'll get you to discuss different, like, the different peak strengths, yeah? And this is just sort of, oh wait. Yeah, most of the peaks that you'll deal with are strong, maybe medium at times, and most of the time will either be broad or narrow, yeah? So these are the different ways we can characterize them if they want you to, like, name what the bond, like, how we describe this trough. These things are called troughs, yeah? The other thing I want to point out before I move on is this region over here, yeah? This region is called our fingerprint region. Everything before 1500 wave numbers, yeah? And here, essentially, the more activity I have in this fingerprint region, the longer the chain is. So here, if let's just say it had like all this stuff over here, like a bunch of peaks, yeah? You'd expect this to be a very long molecule, yeah? But here, this one doesn't have that much activity going on, so it's a relatively short molecule, yeah? So if someone tells you asks you about the fingerprint region, it tells you, they're like, oh yeah, what does the fingerprint region represent? It represents the length of this compound, yeah? Whether we're doing with a really large compound or really small compound. So the more activity in that region, the larger the compound. So here, this is how they go about naming them, yeah? I would not call this one an NH group over here, yeah? And they have this big peak over here, which represents the OH group, yeah? So I would say one thing about the IR is that you have to practice them to get a lot better at them. I would not call this an OH. Yeah, I would have called this an OH. I would call this an OH alcohol. I would not. I don't agree with the textbook here. Because here it can't like they'll make it very clear on the exam. They won't be ambiguous with it. Okay. No, but that peak just doesn't make sense because it's between here and here, right? Like how the hell does that doesn't encompass the whole peak, yeah? It's not like big enough. So here, right? We have this one. Refer to the IR spectrum in the data IR spectrum. The compound could be, yeah? Continue going King one on 4. Yeah. Right, still finding one. So what's present here? What peaks do we have? Look at everything above the fingerprint region. So here, what do you guys think it is? Is it A, B, C, or D? So one person says A. One person says A. So we have one thing over here, yeah? This represents the O double bond H bond. This represents O double bond. Oh wait, C double bond O. This one over here, yeah, could either be it looks like OH looks like an OH alcohol. However, there's no carbon-carbon double bond with an OH alcohol in this. Yeah. So I'm pretty sure what they want you to do is they want you to pick C here because it contains the OH and an amide, which could also explain this. Yeah. Now, this is a good time to mention that there are some variations in these. The numbers in your data book are not absolute. Yeah. They can have variations of being bigger and smaller, but they should be in that approximate range. So here, C is the answer because it's the only one that makes sense to be the answer. Yeah? If I was actually doing this in an exam, I would have not accepted anyone saying NH2. Yeah? Like in the short answer. I would have expected them to say OH alcohol here. So does that make sense for everyone? It's not this one here because this is a C double bond O. Oh wait, C. Wait, shit, it's an extra C. So we have here C double bond O C. There's nothing explaining this peak in this compound over here. Is that all good? Thumbs up, thumbs down, thumbs to the side. Okay. So, which one of the following statements about IR spectroscopy is correct? IR is only absorbed at one wavelength, and IR spectrum can be used to identify the mass of a spectrum. An IR high transmittance corresponds to high absorption. IR spectrum can be used to determine the type of bonds in an organic molecule. What do you guys think? A, B, C, or D? Abacadabra. One person saying D. We have a second person saying D. We have a third person saying D. We have a fourth person saying D. Do we have a fifth? We have a fifth person saying D as well. Holy shit. Yeah, so D. No, we know that it does it at multiple wavelengths. A wave number represents a wavelength here. Yeah, so it happens at multiple wavelengths. We haven't even spoken about it being able to determine the mass. Yeah. C, transmittance is the opposite of absorption. Yeah. So here, if it was a high transmittance, it was a low absorbance. Yeah. And D is literally the definition for IR spectroscopy. It helps you determine the bonds present in organic molecules. So here, in the IR spectrum of a carboxylic acid, there's most likely to be an absorption peak at, what do you guys think? A, B, C, or D? So one person saying A, one person saying C. What about everyone else? What are you calling? We have C. We have C. Wesley, what do you think it is? A, B, C, or D? C. Yeah, it's C here. Yeah. This one is outside the ranges given in the data book. So if you look at the data book for the alcohol of the acid, it'd be 680 to 740. So we wouldn't expect it at here or here. And then we wouldn't expect it at here because this only goes from 2500 to 3600, right? That's the OH alcohol. So here, which one of the following semi-structural formulas is consistent with the spectrum shown above? So what do you guys think? Which one of these corresponds with something shown above? What do you guys think? A, B, C, or D? There's two answers I'll accept here. D, yeah. D. C. So, yeah, technically it could be B or D, yeah? Technically D is the more correct answer, and I'll explain why, yeah? So here, this part represents a C double bond O bond, yeah? We don't know what type it is, we don't need to label what type it is. Because there's nothing over here, right? It can't be C, yeah? So does that make sense, Swayhan? There's nothing on this part of the graph that indicates the presence of an alcohol or carboxylic acid. So it can't be that. Now, it can't be A, right? Because we know that there's a C double bond O, so it's between B and D. Now, technically, D is the correct answer because of this peak here. And this peak here represents a CO bond, but this isn't in the data book anymore. So if on the exam, if they put this, they would have accepted B or D as the answer options. Yeah? Technically, D is the more correct one because of this peak over here, but you don't know that peak. I do because I'm a big nerd. So, here. Which one of the following are present in the unknown compound? What do you guys think? A, B, C, or D? So we have one person say B. What does everyone else think? B or D? Bibbida or dibbida? Bibbida, bibbida. B, B, B. B. So here's B. Yeah? The reason being is that the only things that we know are present are this and this. There's no way we can determine if either of these two are present. Like, well, like here, we could say that it's present because we have this OH, right? But it could be like it could just look like, I don't know, it could look like this. We have no idea, yeah? So we can't determine the presence of these two bonds, yeah? So it can't be C, it's definitely not A, and that means it's definitely not B because we cannot determine the presence of this one, right? If it was this one that was present, it'd be between this and this, which is extremely small. You'd expect a peak that looks something like this over here. Well, so does the infrared stuff make sense? So they identify the bonds. So the first thing, the mass spectrum helps you find the mass of the compound. The the IR spectroscopy or the IR spectrum helps you find out what bonds are present. Yeah, but you have to type that out each time. I have the slide here for a reason. So, maybe just understanding this idea of carbon equivalent carbon environments and non-equivalent carbon environments. Yeah. So equivalent carbon environments mean that they are the same. Non-equivalent ones means they are different carbon environments. Yeah. And this is called carbon-13 NMR, or what does NMR stand for again? Something magnetic. What does NMR stand for again? You don't need to know this. I'm just trying to remember. Nuclear magnetic resonance. There you go. It stands for nuclear magnetic resonance. So, here, right? This is what a mass spectrum does. Essentially, right? What we're doing is that we're shooting radio waves into the compound, and that's causing and that will cause the carbon atom to vibrate in a specific way. So we're focusing on the specific carbon atom, yeah? And here, depending on how it vibrates, it will tell us how many environments are present. Now, you've probably never heard this word environments before, and we'll get onto that one. We'll get onto that word environments in a second. But here, if there's 3 peaks, that represents there are 3 environments. Yeah. So that's the big thing that we want to notice. Yeah. And the other thing that we want to notice is that here the area under these curves represents. I'll explain what the TMS is in a second. Yeah. But here, the area under these curves represents the ratio between them. So this is approximately a 1:1:2 ratio. So that means in this environment here, we should only expect one, like if there's 1 carbon in this environment, there's going to be 1 carbon in this second environment, and there's going to be 2 carbons in this third environment. Both trying to do my job over here. Trying to take my role. It could easily be 2, 2, 4. Yeah, there could be 2 carbons in one environment, 2 carbons in another, and 4 carbons in this first environment. Yeah. Now, the TMS is basically our relative point. Yeah, that's just where we begin from. It's whatever the machine is calibrated to is the TMS. Yeah, it's basically like our 0 point. I'm pretty sure TMS stands for like ethyl something something. Yeah. But you don't need to know that. It's more or less, can you understand what the graph is trying to tell you here? Yeah? So here, what you can see is that, well, we have a peak with a chemical shift of about 1, 2, 3, 4, 5, 6, 7, 8, 9. Wait, 1, 2, 3, wait, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8. What? 1, 9. Wait, is it 5, 10, 15, 20? What the fuck is this scale? Yeah, you can't read that scale. Okay, that's a weird scale. Because it's like it's like broken up into 9 pieces. Which doesn't really make sense to me. Anyway. We'll move past it. So here, right? What are all of these? If you go back to your best friend, the data book, right? It has this pet table down here, table 22. And these are all of our carbon NMR ones, yeah? So down here, this is all of our carbon NMR stuff. And essentially, it tells us what could be causing each one of these peaks. Let me just switch back to this one. So what could be causing each one of these peaks? So here, this peak is at about, I would say about like 70 to 80, yeah? We have about a peak from 70 to 80. I can't really tell because the scale is really bad. But essentially, I go into my data book and I see, well, what matches that same thing, yeah? We have this, it could be these bonds here. It could be these bonds over here. It could be this one over here, yeah? So we have 3 things it could be, yeah? And keyword, it could be these, but it also could not be these as well, yeah? We can't be completely sure. It just suggests what could be there. That's the key thing. It suggests what could be there, yeah? If we look at these 2 over here, if you look back at your data book, you'll see we have the if you look back at the data book, yeah, you'll be able to see that about, I would say that's about 35, maybe 35. It's a really bad scale again. If we look back at the data book here, we want to look for things that are between 35. So I'd say this one over here, this one over here, maybe this one, and maybe this one on the lowest end, yeah? But the key thing, those could be there, but we can't be sure. So here, if they ask you this sort of question, they'll just say, oh yeah, what is a possible environment that this could be, yeah? And I'll discuss environments a little bit more, yeah? So does that make sense for everyone? Any questions about that? It's just suggesting what could be there based on the graph. Thumbs up, thumbs down, thumbs to the side, thumbs on the ground. What do you guys think? What about Emes and Mia? What do you guys think? How does IR Spectro does that? What do you mean? How does IR Spectro do that? We're not looking at the IR.
No. I'm asking like, doesn't like IR spectroscopy does the same thing?
No.
Like it helps you determine the organic.
So IR spectroscopy uses infrared light to vibrate the bonds. Yeah. NMR uses what's it called? Like magnetic resonance to vibrate the actual particle itself. So here it's vibrating carbon. Yeah.
Yeah.
So and one finds the bonds between molecules. The other is more about the environments that are present, how many environments that are present. Yeah, because you don't know that environments part that well, that we haven't, that you don't, that it doesn't fully make sense. So I'm going to discuss this idea of environments. Yeah, here, what an environment refers to is what the neighbors are bonded to. Yeah, so here, this carbon, I want to see what environment it's in. Yeah, we can see that this carbon's bonded to 3 hydrogens. And it's also bonded to this carbon, which is bonded to which is bonded to 1 hydrogen, which is bonded to this carbon, which is bonded to 2 hydrogens, bonded to this carbon, which is bonded to another 2 hydrogens, which is bonded to this carbon, which is bonded to 3 hydrogens. Now the big thing here is that I'm looking at the whole molecule when I'm determining the environment that it's in. Yeah. So this one we'll just call this an environment 1. Yeah. This one over here. Oh, actually, sorry, I forgot to mention something. Yeah. So this carbon's bonded to this one, which is bonded to 3 hydrogens. However, this one over here is bonded to one carbon, yeah, and also 3 hydrogens. But this carbon is also bonded to a carbon with 3 hydrogens, and a H. This carbon is bonded also to another carbon, which has 2 hydrogens. This carbon is bonded to another carbon, which has 2 hydrogens, and this carbon is bonded to one with 3 hydrogens. Do you see how those two are the same as each other? They have the exact same environment. Yeah? We call these equivalent carbon environments. Yeah? Equivalent carbon environment. Does that make sense? Right? They're equivalent carbon environments. Yeah? We're looking. The big thing here is that we're looking at the whole compound. Yeah? I'm not just looking at the neighbors, I'm looking at the neighbors' neighbors, and the neighbors' neighbors' neighbors, and the neighbors' 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 neighbors. Yeah? Here, if I was looking at this carbon over here, I'll just clear everything. Yeah? If I was looking at this carbon over here, it's bonded to this carbon, which is bonded to 3 hydrogens, this carbon, which is bonded to 3 hydrogens, and this hydrogen. Yeah? This is bonded to hydrogen, a carbon, a hydrogen, a carbon, and a hydrogen, carbon. So do you see how that's completely unique compared to the rest of these? Yeah? Same with this one, yeah? Even, like, you might say that 3 and 4 are the exact same, but 3 is bonded to a carbon, which is bonded to 2 hydrogens, yeah? Which is bonded to 3 which is, each of these are bonded to 3 hydrogens, and then a hydrogen. Whereas this one is bonded to this hydrogen, which is in turn bonded to it, yeah? So they basically, for it to be an equivalent environment, it needs to basically be the exact same. Yeah? This is like these carbon environments, they're new to you, yeah? So don't stress out too much if you don't fully understand them. We'll discuss them a little bit more in chirality, yeah? Like, and how they actually affect a compound, right? But I want you to remember the idea of the environments consider all of the neighbors, yeah? So if we look at this compound here, right? This has the exact same environment as this because it's bonded to a CH2, which is bonded to a C, which is bonded to a C, which is bonded to CH2, which is bonded to the C1, yeah? We can say the same thing about this one if we go backwards, yeah? If let's just say we put like an OH in here, right? These two would be different environments, yeah? This one would also be a different environment from this one. This one would also be a different environment from this one, yeah? And it's because if they have different proximities to these OHs, yeah? They have different proximities to these OH groups. So, does that make sense? Does anyone have any questions about that? Any comments, any concerns? Yeah, you do? What's up? He does not. He doesn't. He's replying to me. Okay, yeah. So here, right, we'd expect this compound to have 5 peaks, and we'd expect this compound to have 3 peaks on our NMR. So here, right, this is for 2-methyl pentane. So we have a pentane, and then our methyl group on the second carbon. Yeah. We can see that this compound here has 5 carbon environments, right? We have one for each one for these two. Yeah, so these two share an environment. We also have one for this one over here. We have one for this one over here. We have one for this one over here. And we'll have this one for this one over here. Yeah? So we have 5 environments, which represents the 5 peaks here. Yeah. This is 5 peaks, isn't it? Yeah, 5 peaks, yeah. Does that make sense to everyone? Does the carbon environments make sense? Or does anyone have any questions about those carbon environments? What about you, Blessing, and you, Slayer? What do you guys think? Yeah, what's up? Hit me with it, Slayer.
Is that middle peak bigger because there's 2 carbon environments that share the same thing?
Yeah, no, it's not about how if it's taller. This has a larger peak. This has a larger area under the curve. So we're thinking area under the curve. Yeah.
Okay, yeah.
So here, it's a larger area under curve. That's why it's like we represent that by showing it's taller, though. Yeah. So here, right? I'll just ask everyone, what compound could this be? Yeah, is it A, B, C, or D? So here, I want you guys to have a think through this. Yeah, how many carbon environments does it have? Yeah, and how can we determine which one has that many carbon environments to it? What do you guys think? Is it A, B, C, or D? Who's gonna type first? Who's gonna type first? Ooh, spooky. B? Okay, we have one person saying B. One person saying B. We have a third person who says B. If you guys are wrong, I'm just kidding. I'm just playing, guys. Chat. I'm just playing. So, we have another person saying B. Okay, so here, this thing has 5 carbon environments. Yeah. So 1, 2, 3, 4, 5. There's 5 peaks. There's 5 carbon environments. So first, how many carbon environments does each one of these have? So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. B's out. Yeah. 1, 2, 3, 4, 5. This one could it be? 1, 2, 3, 4, 5. So this one could be. So it could be either of these two. Yeah. Now, how do we determine that? We look at the chemical shifts. Yeah. What could cause this 140 chemical shift? That's like the close to 140 chemical shift. Let's have a look. So we'll share this tab instead. Yeah. what could be causing this 140 chemical shift? We can either see it's a C double bond, yeah, or an this, which is a ringed compound essentially. So this is a benzene ring here, yeah, that could be causing that. So here it has to be most likely this one. So what we should expect over here is we should expect a double bond. So here we should expect this double bond. The only one that does it is D, yeah? The triple bond can't be explained using anything in our data book. So the closest answer is going to be D. Does that make sense? The other ones don't have double bonds. That's why I haven't considered them. So okay. So the 13C NMR spectrum of an unknown organic compound has 3 distinct peaks. How many carbon nuclei does the compound have? Has 3 distinct peaks. How many carbon nuclei? D, B, bum, 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 B. Emeth, can you explain why you changed your answer to D?
Um, it's a bit difficult because you can't say that there's just 3 peaks because there's like usually a value underneath like these peaks, but we don't have that value, so we can't necessarily determine it.
Yeah, so here it's D. We know that there's 3 distinct environments, but we don't know how many carbons in each environment. So there could be 3 carbons in each environment, yeah? There could be 5 carbons in each environment. There could be one of them with 1 carbon, one of them with 2 carbons, the other one with 6 carbons, yeah? We can't determine how many carbons that we have. All we can determine is how many environments that we have, yeah? So here, what are 2 possible carbon environments that could produce the peak at 168 ppm? So what are 2 things that could produce the peak at 168 ppm? If you look in your data book, you'd be able to find it out. Let's do Socrates taught me Percy. Yes, it's such taste. I swear on God, for real. I can't decide whether we should live that. But we go there. Okay. What do you guys think? And you'll be like, I don't know where any of these peaks are. Use your freaking data booklet. D A. Okay. Can it be? I've never truly believed I would break my family's heart. Okay. Enough singing from me. So, the answer is A here. Yeah? It can't be singing A and A. Bro, shut up. Okay? God forbid a man sings. These 2, right? Aldehydes have a very high ppm. So it's almost like 190, 195. Yeah? Very high. And here, this alkene is 110 to 150. That can't explain a chemical shift at 168. So the answer here is A, most likely. So, have a go at this one. The unknown compound contains 5 equivalent carbon environments, 5 non-equivalent carbon environments, 6 equivalent carbon. How many does it?
Hello? What?
So BBB. Anyone else? Anyone else want to start rapping? Start rapping the B's. Start rapping the b. Uncle's cooking like that. Uncle's not. Shut up, bro. Shut up. Okay. Yeah, the answer is B. It's just this one. So yeah, we have the 1, 2, 3, 4, 5 environments, and they're non-equivalent. If they were equivalent, yeah, then we'd talk about how many carbons there are in total. So here, this is like a 1 to 2 to 2 to like. This is such a weird ratio. Anyway, it's fucked up. Don't worry about this. Here, how many peaks would it be expected to appear in the CNMR spectrum of this compound? How many would you expect to appear in the CNMR of this compound? Who knows? Three. So D. So I have one person say A, one person saying D. What does everyone else think? B, okay. You can't guess like that. So we have these two environments are the exact same. Because if I look at them and I see what they're connected to, it's the exact same as one another. Yeah? So here C is bonded to a C, which is bonded to this C and this C. One's by a double bond. This C is bonded by this C. This C is bonded to a C. This one's bonded to C. This one's also bonded to another C. Yeah? So the exact same. Yeah? These two are also the same. Yeah? Because they're bonded to the exact same things. They're basically symmetrical to one another. Yeah? Here, this one is the same as this environment over here. Yeah? Because if we go around, they're bonded to the same things, the same ways. Yeah? Wait, no, that's wrong. No, that's wrong. No. It's this one is the same as this one, and this one is the same as this one. So the answer is actually B. Yeah? It will take you guys a bit of time to figure out to get these environments. But does that make sense for everyone? Like, this isn't a... Anyone else besides Kavinu? Mia, Swayam, Keith, Wesley. Okay. So we now have HNMR, which basically works in the exact same way as CNMR. But there's high resolution and there's a low resolution. Yeah? There's high resolution and there's low resolution. And the only thing you really need to know here, you don't need to know these definitions. All these definitions apply. So here, with low resolution, it will look basically the exact same as a C NMR. So they'll tell you in the question, you're looking at C NMR or a H NMR. this means this compound has 3 hydrogen environments, yeah? So here, we can tell the ratio of protons to one another. So here, this is a 2 to 1 to 3 ratio, yeah? Right, so that means there's 2, for every 2 environments in one, there's 1 in this one, and there's 3 in this one, yeah? We can also tell that, like, what could be that compound, yeah? So here, if we look down here in our data book, we might be able to tell what this compound is. So this could either be, this compound looks like it might contain an RCH3, 2. This one could be a CH. Okay. Wait, no, that doesn't work. Okay. Wait, frick, none of these work. Oh, yeah. This one could be a ROH. And this one over here, 3, could be a... What could this one be? C... better. It could be a C... Oh, that's too high. No, it's not my bad. This one could be an RCH2OH, or yeah, it's that. RCH2OH. Yeah. So these are possible bonds that this could be to form this to form this environment. Again, these are possible bonds. We have no idea if these are the exact ones. So let me just go back to this screen share. Right, that's what I was writing over here. Right, we're using that table to find out what possible bonds it could be. Yeah, we're not saying these are the bonds. We're not sure. Yeah, the question has to give us more detail if we're going to be using these. This helps us find the number of hydrogen environments. Now, they've included this thing called the integration curve. Basically, they draw a literal integral and you just measure the length of the integral. So here, right, the integral has a 4 to 2 to 6 ratio, yeah? That means the ratio of protons or of hydrogens in each environment is going to be 2 in this environment for every 1 in this environment for every 3 in this environment. That's literally what the integration curve is, yeah? You measure it out with the ruler and you find the difference in the lengths. It's great, isn't it? Very scientific technique. Incredibly scientific. So does that make sense for everyone? Can I get like a thumbs up, thumbs down, thumbs to the side? What do you guys think? Okay. So, yeah, this is the thing I wanted to say. It's not about the height, it's about the area under the curve, yeah? It's about the area under the curve. That's why they use an integration curve to represent this. Because integration represents areas, yeah? Integration represents areas, yeah? So we use an integration curve. It's not about the height, yeah? The height doesn't matter, yeah? It's about the area under the curve, which they show off using that integration curve, yeah? So, here, if we tell the ratio of these ones apart, we'd have to say that there's a 1 to 2 to 3 to 3 ratio between these, yeah? That's if I measured them with a ruler, yeah? So if I look down here, is there 1 to 2 to 3 ratio? No, it doesn't look like there is. So my guess is it has to be D, because it's 1 to 2 to 3, which could be turned into 0.5 to 1 to 3, to 1.5, if I divided everything by 2. Does that make sense? Is there any questions about that? I'm literally, like, if I had my ruler here, I would grab my ruler, I'd put it on the page, I'd measure the length, and I'd be like, this is half of this one, which is half of this one, yeah? Which is like, and this one is 3 times this one, or something like that, I don't know. Stupid. Yes, so the big thing, yeah? These are the 2 big things that I focus on. telling you the number of non-equivalent environments, yeah, so the distinct peaks, as well as potentially what is present, potentially, yeah. It's a possible indicator. We can't be sure. The question will have to provide you more detail, or it would just say suggest, yeah. If it says suggest, you can throw basically anything that makes sense, yeah. I swear to God, if anyone puts here an arithmetic ring, I'm going to explode because we don't cover them, yeah. So this is high resolution, yeah. High resolution has its difference. It basically shows the same pieces of information, but it has this thing called splitting, yeah. And splitting tells you how many how many hydrogens there are on adjacent carbons, yeah. So we have here H, 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 C, H, H. Let's imagine we have this compound, yeah? Can Mia, how many environments or how many distinct environments are there here? Or non-equivalent environments?
Oh, did you speak 3?
3? No, not quite. Kavinu, what do you think? How many environments are there? I think we lost Kavinu. I'm lagging. Well, what's everyone in like just dying laptops, bro? Whatever you Swayham, what do you think the number of peaks there are here are? How many distinct peaks there are?
I was gonna say 1.
There's 2. So these ones all share an environment, yeah? And these 2 share an environment. Does that make sense why for the 3 people that I asked? Okay. So here, right? The splitting, so here, these 2 hydrogens, so the blue hydrogens, are bonded to this carbon. And we want to see what's bonded to adjacent carbons, yeah? So here we have this one's adjacent and this one's adjacent. Basically, the neighbors, yeah? Here, right? The splitting pattern tells you how many hydrogens are bonded to these adjacent carbons. So in total, we have 6 hydrogens, yeah? So we have 6 hydrogens. How the ppm shift, how the high resolution represents this is they had 7 splits, yeah? It follows this n+1 rule, yeah? Where the number of splits is 1 more than the number of hydrogens on adjacent carbons or neighboring carbons. Adjacent or neighboring, that's the phrase you want to use. Adjacent or neighboring, yeah? So does that make sense for everyone? Does that make sense? The 7 splits. For these 2 environments, if we look at the ones on adjacent carbons, we'll see that there's only 2. So how many splits do you guys think it will have? How many splits do you guys think it will have? Right? In the actual graph, how many splits do you think it will have? Type it in the chat. What do you guys have? So how many splits do you think the red hydrogens will have? No one? No clue. It's gonna be 3, yeah? Because if I don't know why this is. We have it C, 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 H, 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 yeah? There's going to be these, the ones in the black, yeah? Oh, wait, I dropped the H. So these ones are all in the same environment. But if we look at the adjacent carbon to both of them, they both have the same adjacent carbon, yeah? So here, right? these H's are going to be the ones that are adjacent to it. Yeah. So here, this one's going to have a 2 plus 1 split, which means it's going to have a splitting pattern of 3, a triplet. Yeah. Now the big thing that I want to point out here is that the neighboring carbon must be a distinct environment. So for example, if we had this one here, yeah, this only has one hydrogen environment to it, yeah. So if I go over to the one with adjacent carbons, it's not a different group of hydrogen environments. So we will not get a difference. We'll only get a split of 1, right? Using that n plus 1, because there's 0 neighboring hydrogens on adjacent carbons that are in different environments. Yeah? Does that make sense to everyone? Any questions, comments, concerns? Okay. So here, these are the different splitting patterns. They're most likely to just give you a table. You just need to know what a singlet, doublet, triplet, quartet, quintet, sextet, and septet are. Yeah. You just need to know what they are. So this represents 1, 2, 3, 4, 5, 6, and 7 splits. So here, if something has a septet split, that means in adjacent carbons, there's 5 hydrogens. On adjacent carbons, there's 6 hydrogens. There's 5 hydrogens for a sextet. Yeah. For a quintet, there's going to be 4. For a quartet, it's going to be 3. For a triplet, it's going to be 2. For a doublet, it's going to be 1. And for a singlet, it's going to be 0. So, does that make sense? So, if you look at this one, yeah, this shows you how many hydrogen environments there are. So again, we look at with everything that the hydrogens and neighbors. We took the neighbors of the hydrogens, the neighbors of the hydrogens, and the neighbors of the hydrogens. Yeah. So all of these hydrogens, all of these 3 hydrogens have the same neighbors, and neighbors, and neighbors. Okay. These 2 hydrogens have the same neighbors. They have the same neighbors. They have the same neighbors. And same with these 3 over here. Does anyone have any questions about the hydrogen environments or determining how many environments there are? Thumbs down as you don't have any questions, or thumbs down that you do have questions? No. Okay. So, Emeth, can you explain why there's 3 environments here? Hello? Can't explain. What about you, Kavinu? Can you explain why there's 3 environments here? I just understand it. Does anyone want to explain it? But unmute your mic and explain it. I don't want to full text this.
Explain how many hydrogen environments there are.
Yeah, no. Why there's 3? Why is there 3 here?
Because on the left side, the hydrogens are bonded to a carbon, which is bonded to a carbon, and then the whole middle chain, and it's repeated twice, so they would have the same environment.
Yeah.
But the carbon in the middle is bonded to a C, which is bonded to a O, which is bonded.
No, we're talking about the hydrogen environment. Sorry. Hydrogen.
Yeah.
Yeah. So here.
The hydrogen in the middle is bonded to a carbon, which is bonded to an oxygen, which is bonded to another hydrogen, and then it has the 2 branches on the either side, which is different to the third one because the other ones, it goes a hydrogen to oxygen instead of a carbon, which means that's another environment. So there's 3.
Yeah. So this one goes hydrogen to oxygen, and then oxygen to carbon, and then carbon to carbon, and carbon to carbon. So, does that make sense for everyone? Thumbs up, thumbs down, thumbs side. What do you guys think? Okay. Very intriguing response. But are you gonna just like sledge each other the whole time? Got one more of these I gotta run. Oh yeah, so here, right? This one, if I drew this organic molecule out, it's gonna look something like this. Cl, Cl. Yeah? This is what this organic molecule is gonna look like. However, right, so if I go through this one, yeah, I'm gonna see that there's one environment here, that there's one hydrogen environment here, and this one has the same hydrogen environment because they're basically symmetrical to each other. Yeah. So here, essentially, if you can find a line of symmetry, it makes it very easy to find how many environments there are. Yeah. Because if, like, let's just say we have a line of symmetry like this, we have like H, 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 and H, yeah? You can see that there's a line of symmetry there, which means that these ones are all in the same environments as these ones, and these ones are all in the same environments as these two over here. So we have two environments for that butane. So I'll keep moving on. So here, the H NMR spectrum of an organic molecule has three unique sets of peaks: a single peak, a 7-peak septet, and a double peak. The compound is, what could this compound be? Right? We know that there's 3 peaks here. So what do you guys think? There's a single, a septet, and a doublet. What do you guys think? A, B, C, or D? What the fuck did this shit even... Anyone else have any guesses? Pop E, okay. What about Mia, Blessing, Kavinu? What do you guys think? B? Yeah. Try and draw out these compounds if you're struggling to do them. I freaking draw when you're rushing. Nah, bro, you got 2 seconds in your exam. You got to answer each question in 2 seconds. Come on. Pick up the pace. Pick up the pace. So here, the answer is B. Yeah? If I draw out each one of these molecules, so draw at A. So A looks like this. So this is what A looks like, yeah? We can see that A actually is 4 environments. So it has 1 here. So 1, 2, 3. These ones are all in the same environment as well, yeah? Because they are bonded to the same thing. They have the same neighboring stuff, yeah? They have the same neighbors and the same neighbors' neighbors. This one is in another environment, yeah? These two, oh wait, let me go back. Blue. These two over here are in the same environment. And then this last one over here is in its own environment. So there's 4 environments there. So it can't be B, yeah? So C looks something like this. So CH3, I'm going to put CH3, CH3, yeah? All of these ones are in the exact same environment, yeah? Because they're all bonded to the same neighbors and to the same neighbors' neighbors. So it's not going to be this one. And then D, right, we have here C, CH3, H3, Cl, CH, and then we have a Cl coming off here, yeah? We have CH2. Here, these two are in the same environment because they're bonded to the same neighbors and to the same neighbors' neighbors, yeah? And then these two are in their separate environments. So there's going to be 2 environments here. So the only one that makes sense is B, because B is the only one that has 3 environments, yeah? And if we drew this out, yeah? If I drew out this molecule, I can show you why it's a singlet, a septet, and a doublet. So here, if I draw this one out, so it's going to look like C, 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 H3, H3, H, and then double bond O, O, H, yeah? This one here is going to have a singlet, yeah? It's going to be a single peak. The reason this one's going to be a single peak is going to be, well, it's going to be a single peak because it's bonded to an oxygen, yeah? And the oxygen doesn't have any hydrogens on it, or it doesn't, like, the carbon doesn't have any adjacent hydrogens on it, yeah? This one over here, H, is going to make up the septet because its carbon is bonded to these adjacent carbons, which have 6 hydrogens in total. And remember, if there's 6 hydrogens in the neighboring, that means there's 7 in the peak because of that N+1 rule, yeah? Over here, the doublet, yeah, is going to be made up from these two because their adjacent carbon is going to be this one, yeah? This one contains 1 hydrogen, so that means by the N+1 rule, we're going to have 2 peaks. So it's going to be B here. Does that make sense for everyone? You put the thumbs. Is that all good? Thumbs up, thumbs down, thumbs to the side. Okay. So, for question 1, in HNMR spectroscopy, the integration curve provides information about the number of neighboring protons, the splitting pattern, the chemical shift value, the relative number of protons in different environments. What do you guys think? So 1C. Anyone else? We have C. What about Mia, Blessing, Soyan? What do you guys think? D. Another C. So, Kavinu, can you explain to me why D is the correct answer? C isn't.
Why D is the correct answer?
Yeah.
Hmm. I don't know.
Swayam, can you explain it?
I was gonna say like the area underneath tells us like how much hydrogens are present in each like environment, if that kind of makes sense.
Yeah, because the integration curve represents the ratio, helps you find the ratio. So if the integration curve is going to be like 1, which is like 1 centimeter, right? And they have a second one, which is 2 centimeters, yeah? That means in this environment, there's going to be 1 hydrogen for every 2 there are in this one. So it doesn't tell you anything about the chemical shift. It doesn't tell you anything about the splitting pattern. It doesn't tell you anything about the neighboring carbons, yeah? So that's why, yeah. This is why you guys don't copy the answer option of each other. Gotta be like free thinkers, you know? Does that make sense for everyone? It can't tell you the chemical shift values. So here, which one of the following regarding splitting patterns in HNMR spectroscopy is correct? The splitting pattern provides information about the number of neighboring protons. The splitting pattern determines the number of neighboring carbons. The splitting pattern is independent of the number of neighboring protons. The splitting pattern is determined by the chemical shift. What do you guys think? A, B, C, or D? So there's A. Anyone else gonna say anything else? Maybe another answer option? Yeah, so here, the answer for this one's just A. Yeah. We're not dealing with the number of carbons. We're talking about the number of neighboring protons or hydrogens on neighboring carbons. It's definitely not C because it's dependent on this. Yeah. And it's not D. Chemical shift, like a lot of the time, the chemical shift doesn't really mean anything. The chemical shift could tell us what the possible bonding could be. Yeah. Which one of the following is not a valid application of the N+1 rule? So what do you guys think? Is it A, B, C, or D? So C. C. Mia, Blessing, what do you guys think? Yeah. So I would have accepted two answer options here, C and A. So C, determining the number of non-equivalent proton environments. It doesn't really help you find the non-equivalent ones. It definitely helps you determine the nature. Identifying the nature of neighboring protons. It does help a little bit with that, and so does D, right? So this less so, D completely, yeah. But I would say A and C are the correct answer options here. And here, a compound shows a single peak in its HNMR spectrum. What can be concluded about the proton in the compound? As a single peak. What does that mean? Yeah, it's A. Remember the N+1 rule. Yeah, there's a single peak, which means N+1 equals 1, which means N equals 0. Which means it has 0 neighboring carbons over here. Yeah? Does that make sense? Any questions about that? Is that all good? Thumbs up, thumbs down, thumbs to the side. So, I'll just stop the recording here.